Hello everyone. Today we are going to discuss about dimension. Today we are going to discuss about dimensional analysis, hydraulic models, and similitude. These are the contents which we are going to cover today. Firstly, we'll look at hydraulic models and why do we need them. Then we will look at the different type of similarities between the model and prototype. Firstly, we'll look at geometric similarity, then kinematic similarity, and then dynamic similarity. After that, we'll look at some of the forces which are important forces which are acting on the fluid flows, which generally we encounter in fluid flow problems, such as the viscous force, gravity force, pressure force, elastic force, and surface tension forces. Then we will look at some non-dimensional parameters such as Reynolds number, Froude's number, Euler's number, Mach number, and Weber number. And we'll also discuss their significance. And at the end, we will discuss about two type of model laws, that is hydraulic model law, and that is the Reynolds model law and Froude's model law. Based on this model laws, we achieve the scaling of models and prototypes.
The first thing is prototype. A prototype is nothing but the actual structure or machine which we design or which we intend to design and construct. Let us say there is an actual dam which has to be constructed in this way. Now this actual real structure would be termed as a prototype. Now these structures are one of a kind structures like dams, spillways, weirs, etc. And their performance has to be evaluated before the direct and actual execution. So in order to validate their performance under the design conditions, their scaled replicas are constructed in the laboratories and they are tested. In this way, these scaled replicas of the actual structures or machines are termed as models. Construction of models and testing of models is a very important part in execution of any project, because without models it is very difficult to predict the performance of the prototype in actual conditions. In order to achieve complete similarity between model and prototype, three types of similarities are essential. Out of that, first is geometric similarity, second is kinematic similarity, and third is the dynamic similarity. So let us try to understand this type of similarities. The first similarity, that is the geometric similarity, as the name suggests, is said to exist when the ratio of corresponding linear dimensions between the prototype and model are equal. So let us say, for example, here you can see a prototype of a building, and let us say its dimensions are, this dimension I will call as LP, where P represents the prototype, and I will call this dimension as BP. The corresponding dimensions in the model, I will say that they are LM and BM. Now, in order to say that they are geometrically similar, both of them, the condition is that LP upon LM should be equal to BP upon BM, should be equal to LR. This LR is called as the length ratio. The second type of similarity is called as the kinematic similarity. Now it deals with the similarities of kinematic quantities like velocities and accelerations. Now let us say, in order to understand this similarity, let us say that the velocity of prototype, the velocity in prototype at a particular point is, let us say, Vp1. We will call this as Vp1, and this velocity is suppose Vp2. So these are the velocities. These are the velocity vectors in the prototype, which are showing the direction as well as magnitude of the velocities. Let us say that corresponding velocity vectors in the models are Vm1 and Vm2. Now, we can say that both the model and prototype are kinematically similar only when this ratios, that is the Vp1 upon Vm1 is equal to Vp2 upon Vm2. This particular ratio is called as will be termed as the velocity ratio. We have to keep in mind that velocity is a vector quantity, so the ratio of directions should be equal, as well as the directions of the corresponding velocities should be similar. Also, for kinematic similarity, these acceleration ratios should also be equal, that is AP1 upon AM1 should be equal to AP2 upon AM2. That ratio we will call as acceleration ratio. One more thing regarding the geometric similarity is that the length ratio, from the length ratio we can also calculate the area and volume ratios very easily, as area ratio will be area in prototype upon area in model, and area in prototype is the square of length in prototype. It is the multiplication of two linear dimensions. So that's why I will write LP square upon LM square. So that is nothing but LR square. So area ratio is the square of length ratio, and volume ratio will be the cube of length ratio. The last type of similarity is the dynamic similarity, and it deals with the ratio of forces. Dynamic similarity is said to exist between the prototype and model when the ratio of corresponding forces in the prototype and model are same. So let us say if Fi represents the inertial force in prototype, and Fi of M represents the inertial force in model, then this ratio should be exactly equal to the ratio of other corresponding forces, like let us say gravity force. So Fg in prototype upon Fg in model, and so on. So these ratios will be called as the force ratio, Fr force ratio. Now we will have to discuss about the dynamic similarity a bit more, because this is the most important type of similarity. And one thing is for sure, one thing we have to understand, that it is very difficult to make a model and prototype dynamically similar. And now we'll see what are the aspects related to the dynamic similarity in some kind of details.
Hello friends, today we are here to discuss more about dynamic similarity, and before getting into dynamic similarity, we are going to discuss about the various forces acting on a fluid element and some dimensionless numbers. So let us say, for example, now here we can see a flow which is taking place over a spillway. This is an Augie spillway, and a flow is taking place over the spillway. Now if we consider an element of fluid, then some forces are acting on this element, like this particular force which you can see is a viscous force which is acting in the opposite direction of the flow. Again, there is a pressure force which is acting normal to the surface of this fluid element, and then there is a gravity force which is acting vertically downward. So these are some forces which are acting on this element. Now if we draw a force polygon, we will get a polygon like this, and the closing side of the polygon will represent the resultant force acting on the fluid. So in this way, many forces are acting on this on a fluid element when a fluid is flowing, and we are going to discuss about these forces. So out of that, the first force which we are going to see is a viscous force, which is denoted by Fv, and it is given by tau into A. Now we know that when fluid is flowing, then viscosity exists in fluid, and that's why when one layer of fluid is moving on the other layer, then on account of the viscosity, shear stress is generated between those layers. Now this shear stress is given by the Newton's law of viscosity as mu into du by dy. So this is the amount of shear stress acting between the fluid layers, where mu is the viscosity of the fluid and du by dy represents the velocity gradient between the two layers. Now this is valid for Newtonian fluids. So we can find out the viscous forces by this particular formula, mu into du by dy into A, and A is the area of contact or shear area. Again, we are having a next force, which is a gravity force. Gravity force is denoted by F of G, and it is nothing but the weight of the fluid element which is acting vertically downward, and it will be given by m into g, where m is the mass of the fluid element and g is the acceleration due to gravity. The third force which is acting is the pressure force. We will denote it by F of P. Now we know that the hydrostatic pressure acting on a fluid is given by rho into g into h. So pressure is given by rho g h, where h is the height of the fluid above the element. So this is the formula for hydrostatic pressure, and the force, the hydrostatic pressure force, can be given by this pressure intensity into the cross-sectional area. And we know that force, the pressure force always acts normal to the surface, so this force is given by P into A, and it will act normal to the surface of the fluid. The next force is the surface tension force. Surface tension force, Fs, we will denote it by Fs, and we know that at the interface of two fluids, there is the surface of the liquid is in tension. Now this tension is quantified by a sigma, which is called as the surface tension, and it is the surface tension force per unit length of the fluid. So let us say, for example, let us say there is a droplet of water. Now this is a droplet of water cut into half. So this particular length of the droplet, that is the circumference, is under surface tension force, and the surface tension force is acting in this way, and it is denoted by sigma. It is the force per unit length. So if you want to find out the surface tension force, we will multiply sigma into L, where L is the contact length. Then the next force is the elastic force. We will denote it by F of E. Elastic force is given by a product of the bulk modulus of elasticity and area of the cross section. So these are the forces acting on a fluid element, and if we draw a force polygon, then the closing side will represent the resultant force, and the which will also represent the inertia of the moving fluid. So inertia force is given by F of I. It will be given by mass into acceleration of the fluid. So inertia force is actually a pseudo force, but you can imagine it as the force which is required to stop the moving fluid. So more the acceleration of the fluid, the more will be the inertia required to, inertial force required to stop the fluid, and likewise. So these are the forces acting on a fluid element. Now we will see, after discussing the forces, now we will discuss something about the dimensionless numbers. Now there are various dimensionless numbers like the Reynolds number, Froude's number, etc., which govern or which affect the flow in particular situations in fluid mechanics. So we'll discuss these numbers one by one. So first dimensionless number is the Reynolds number. It is represented by RE. RE stands for Reynolds number. Reynolds number is the ratio of inertia force to the viscous force. So that is equal to Fi divided by Fv. Now we have seen that inertia force is equal to the mass into acceleration of the moving fluid. So mass can be written as mass density into volume, and acceleration can be written as velocity per unit time. But we know that volume upon time is nothing but the volume flow rate, and that is nothing but the discharge. So rho into Q into V we can write, and the volume flow rate can also be written as area into velocity by the continuity equation and into B. So we are getting Fi is equal to rho A V square. Also, the viscous force is given by Fv is equal to tau into A, where tau is the shear stress and A is the contact area, and according to the Newton's law of viscosity, the shear stress is given by mu into du by dy then into A. So we are getting mu into du is nothing but the velocity, is the change in velocity upon change in length. So this is the length into the area. So we are getting mu into, so area is nothing but square of length, so we can write A as length square. So we are getting mu into V into L. So if we take the Reynolds number, Re will be equal to Fi by Fv is equal to rho A V square upon mu into V into L. So we are getting this again area will be can be written as rho into L square into V square upon mu into V into L. So we are left with rho V L upon mu. So this is the expression for Reynolds number, where rho is the mass density of the fluid, V is the average velocity of the fluid, L is the characteristic length of the problem, and mu is the dynamic viscosity of the fluid. So that is the expression for Reynolds number. Now if we want to calculate the Reynolds number of a pipe, so let us say this is a pipe, and let us say d is the diameter of the pipe, then the characteristic length of the problem will be the diameter of the pipe. So the formula for Reynolds number for a pipe flow will be Re is equal to rho Vd upon mu. So d is nothing but the diameter of the pipe. Now Reynolds number is important in the flows where viscous forces are predominant, like flow through pipes, and flow over the bodies or the external flows, like flow over an airfoil or flow over a cylinder or sphere. Now these are the cases of external flows. So external flows. So Reynolds number will be important in these kind of situations where viscous forces are predominant. The next dimensionless number is the Froude number. Now the Froude number Fr is defined as the ratio of square root of inertia force to the gravity force. So it is equal to square root of Fi upon Fg. Now we know that inertial force is equal to rho a v square, and this Fg, the gravity force, is given by mass into acceleration due to gravity, and we can write mass as mass density into volume into acceleration due to gravity, and volume can be written as rho into A into L into G, where A is the area and L is the linear dimension length. And Fi, we know, we have earlier deduced, is equal to rho a v square. Therefore the Froude number will be equal to square root of rho a v square upon rho a L into G. So rho a will get cancelled, and we will get v upon under root GL. So this is the expression for Froude's number, which is average velocity divided by square root of G into L, where L is the characteristic length of the problem. Now this Froude number is important in case of flows where gravity forces are predominant, like the flow over spillways or open channel flows, like that. So now what is the significance of the Froude number? We can take an example of a spillway. So suppose this is an auger spillway and flow is taking place over the spillway in this form. Now this is the downstream of the spillway and this is the actual spillway. So if we calculate the Froude number here on the location or on the surface of the spillway, the Froude number which we'll get will be more than 1, because here the acceleration of the fluid is more, so inertia of the fluid will be very high, and that's why, as per the definition, the inertia force will be greater than the gravity force, and that's why the Froude number will be very high and it will be greater than 1, and we call this flow as a supercritical flow. And if we calculate the Froude number at downstream at some section here, let us say this is the section, downstream section, if you calculate the Froude number, it will be less than 1, and as per the definition it is the ratio of inertia to the gravity force, and here you can clearly see that inertia of the force will be less, and hence the Froude number is less than 1, and this type of flow is called as a subcritical flow. So in open channel flows, Froude number plays an important role and it determines or governs the flow, and you can actually classify the flow as supercritical, subcritical and critical. So a flow will be supercritical when Froude number is greater than 1. A flow will be a supercritical flow when Froude number will be less than 1, and it will be termed as a critical flow for Froude numbers equal to 1. So Froude number play an important role in governing the flows in open channel in this way. The next dimensionless number is the Euler's number, or EU. Euler's number is defined as the ratio of square root of the inertial force to the pressure force. So it will be equal to square root of Fi divided by Fp. Now the inertial force, we know that it is rho a v square. Now the pressure force is equal to the pressure intensity into the cross sectional area, or the area on which the pressure is acting. So these are the expressions. So if we calculate the Euler's number EU, it will be square root of rho a v square upon p into a. So that is equal to, a will get cancelled, so we are left with v upon square root of p by rho. So this is the expression for Euler's number, and it is important for the flows where pressure forces are predominant in the entire force polygon, and it will determine or govern the flows in those cases. The next dimensionless number is the Weber's number. Weber's number, we will denote it by WB, and it is defined as the square root of inertia force to the surface tension force. So Weber's number will be equal to square root of inertia force to the surface tension force. Now inertia force, again, as we know, it is equal to rho a v square, and surface tension force will be equal to sigma into L, where sigma is the surface tension intensity and L is the length over which the surface tension is acting. Therefore, Weber's number expression would be equal to rho a v square upon sigma into L. So now this a can be represented as rho into L square into v square on sigma into L. So we are left with Weber's number is equal to the square root of rho VL upon sigma. So we can write WB is equal to, it will be V square. So it will be WB is equal to V upon under root of sigma by rho L. So this is an expression for Weber's number. Now Weber's number will be important where the scales of the problems are small, and hence the surface tension forces will become important in those cases, and then the Weber's number will come into picture, and it will govern the flows. The next dimensionless number is the last dimensionless number is the Mach number, represented by capital MA, and it is defined as the square root of ratio of inertia force to the elastic force. So it is equal to the square root of Fi upon Fe. Now Fi, again, we know that it is rho a v square, and elastic force is given by the modulus of elasticity, bulk modulus of elasticity K into cross sectional area. So therefore your Mach number will be equal to square root of rho a v square upon K into A. So we are left with V upon root of K by rho. So this is an expression for Mach number. Now Mach numbers are important where the flows become compressible, and the velocities of the flow become very high, like flow over aircrafts, flow over fighter planes, etc. The design of aircrafts is highly affected by the Mach number of the flows, because it affects the drag force acting on the aircrafts to a large extent. So in these cases Mach numbers will be considered. Now these are all the forces acting on the fluids and the various dimensionless numbers. Now coming back to the dynamic similarity, we can say, so let us consider this picture. Now here we can see a spillway prototype and a spillway model. On the top you can see a spillway prototype, an Auger spillway prototype, and below that there is a model of the same prototype, and the force polygons of both the model and prototype are shown here. Now a model and prototype are said to be dynamically similar when the ratio of all the corresponding forces in the force polygon is same. So the Fg of prototype divided by Fg of model should be equal to the Fv of prototype divided by Fv of the model, and same ratio should be followed by Fi in the prototype to the Fi of the model. So if we want to say that a model and prototype are dynamically similar, then the ratio of all the corresponding forces in the model and the prototype should be same as shown here. Now we can say or derive from this expression easily that let us say we consider Fi in prototype divided by Fi in model is equal to the let us say G in prototype divided by Fg in model. So we can write very easily by just substituting Fi in prototype divided by Fg in prototype is equal to Fi in model divided by Fg in model. But the ratio of Fi and Fg we can say is nothing but the Froude's number. It is actually the square root, but you can take the square root of both the sides and you will get the Froude number of prototype on the left hand side should be equal to the Froude number of the model on the right hand side. So likewise we will get the ratio for all the forces, and therefore we can say that to achieve the dynamic similarity between the model and prototype, all the dimensionless numbers, that is the Reynolds number, Froude's number, Weber's number, Euler's number and Mach number in the prototype should be equal to the model. So if we are saying that a model and prototype are similar, then the Froude number of the model should be equal to the Froude number of the prototype, and also Reynolds number of the prototype should be equal to the Reynolds number of the model, and likewise. So then and then we can say that model and prototype are in complete dynamic similarity. Now in the reality it is a very difficult condition to achieve, because for this purpose we have to match the ratio of all the forces, and it is practically very difficult to achieve. So what we do is we try to match the dimensionless number which is concerned with the force which is predominant. Let us say, for example, in this particular example of the open channel flow, gravity forces are predominant, so we will try to match only the we'll try to match only the Froude number. So we will match Froude number of the prototype should be equal to Froude number of the model, and we will not consider the other dimensionless numbers because they are not affecting the flow as that much. Now this type of analysis, when you apply, these are called as model laws. So this particular law will be termed as a Froude's model law because we are matching the Froude's number. Similar case we can apply for pipe flows also, and different model laws we can achieve, and we are going to see these model laws one by one from hereafter. So the definition of dynamic similarity can be summed up as when the force polygon in the prototype and force polygon in the model are similar, then the prototype and model are said to be dynamically similar. And the implied meaning of that becomes that in order to make the prototype and model dynamically similar, we have to match, or we have to equate, or we have to rather match all the dimensionless numbers in the prototype with the dimensionless numbers with the model. So the Reynolds number of prototype should be equal to the Reynolds number of the model. The Froude's number of the prototype should be equal to the Froude's number of the model. The Euler's number of the prototype should be equal to the Euler's number of the model. The Weber's number of the prototype should be equal to the Weber's number of the model. And lastly, the Mach number of the prototype and model should be same. So if we achieve this condition, we can say that complete dynamic similarity has been achieved. Now this is very difficult to achieve in reality. So we don't match all the numbers, but we match one or the other number which is affecting the flow in that situation. Let us say, for example, if we are talking about a pipe flow and we want to make a model of a pipe flow, then we will equate the Reynolds number, because Reynolds number is the because viscous force is the governing force in that flow. So we will see the laws of modeling one by one. So first law is the Reynolds model law. As we can see here, the Reynolds model law. The Reynolds model law states that the Reynolds number of the prototype should be equal to the Reynolds number of the model. And if you apply this and make a model, then it will be according to the Reynolds model law. So this model law can be applied to flow situations such as pipe flows and external flows. That means flow over bodies, like suppose there is a, let us say, external flow means let us say there is a sphere or any cylinder and flow is taking place over that cylinder, like flow over bridge piers, flow around bridge piers, etc. So if this is the case and we want to make a model of this, then while making a model we should equate the Reynolds number of the flow in prototype and model. So this is an example of a external flow. So now here you are having a prototype and let us say that we have to transport some fluid. It can be, let us say, any fluid like a petroleum product, and we have to transport that petroleum product to a very large distance through very large pipes. Let us say the diameter of the pipes are very high, in the order of 10, and we want to study that flow in the laboratory, and for that purpose you have to construct a model in your laboratory which can simulate the flow in the prototype. Now while making the model of the prototype in this particular situation, it's very difficult to use the same type of fluid, because the fluid, then you will have to use the fluid in the prototype, which may be petrol, diesel, or any oil, etc. Also, you cannot use the diameter of the prototype because it's too large. So in these situations, we know that viscous forces are important. So in order to make the model dynamically similar, we have to calculate the Reynolds number of the prototype by this formula rho Vd upon mu, and this subscript represents the prototype P. So rho P Vp dP upon mu P represents the Reynolds number of the prototype, and we have to match this with the Reynolds number of the model. So rho m Vm dm upon mu m. So if these ratios are equal, then we can say that the prototype and model are dynamically similar. So if we further analyze this, we would end up in rho r Vr dr upon mu r is equal to 1. Now here the rho r is the ratio for densities, Vr is the ratio for velocity, dr is the ratio for diameters, and mu r is the ratio for dynamic viscosities. Now try to understand that there is a very large advantage by of using this Reynolds model law, because you see that if you are trying to study the flow of, let us say, petrol, then it is not necessary that you should use petrol as a fluid in the model, because the flow is not, or rather the modeling is not dependent upon which type of fluid you are using, but rather it depends upon the matching the ratio of forces. So in this case, the ratio of inertia to the viscous force is equal to the Reynolds number, and we are matching the same ratio of inertia to viscous force. So that's why you can use any type of fluid, or rather you can use any diameter of the pipe also. You just have to see that the Reynolds number in both cases is same. So that's an advantage of the model law. So if we go ahead and derive some expressions for scale ratios, then we'll see that. So first is the scale ratio for time for prototype and model. So we know that ratio for velocity is Vp upon Vm, and Vp can be written as length in prototype upon time in prototype, divided by Vm can be written as length in model upon time in model. So the velocity ratio comes as Lr upon Tr. Therefore we can write Tr is equal to Lr upon Vr. So this is the scale ratio for time. Similarly, we can derive the scale ratio for acceleration as AR is equal to AP upon AM, where AP and AM represents the acceleration in prototype and model. Acceleration in prototype we can write as VP upon TP, velocity per unit time, and acceleration for model similarly we can write Vm upon Tm. So acceleration ratio we will get as Vr upon Tr, that is ratio of velocity divided by ratio of time. Now lastly, the scale ratio for force is given by Fr is equal to Fp upon Fm. So force in prototype upon force in model. Now in place of force, we can replace force by mass into acceleration. Mass can be written as mass density into volume. Acceleration is written as velocity upon time. So this volume upon time can be replaced by discharge, that is the volume flow rate, and discharge we can write area into velocity. So ultimately force is equal to rho a v square. So if we use this analogy, we will get force ratio as rho p ap vp square upon rho m am into vm square. So rho p upon rho m will represent rho r, ap upon am will represent lr square, because area ratio will be the square of length ratio, and vp upon vm square will represent vr square, that is the ratio of velocity. So these are the scale ratio for various physical parameters when you are applying the Reynolds model law. The next model law which we will discuss is the Froude's model law. Froude's model law states that the Froude number of the prototype should be equal to the Froude number of the model. Now this model law is applied where gravity forces are important, like the open channel flows, flow over spillways, weirs, etc. Now here you can see the flow over a spillway, and that's a prototype, and suppose we want to make a model of this spillway, then we should apply the Froude's model law, and let's try to apply this and derive some equations. So the law states that Froude number of the prototype should be equal to the Froude number of the model. Therefore Froude number of the prototype is V under root GL. I'm using the subscripts P to represent that all these parameters are related to the prototype. So similarly, Froude's number for model as Vm upon under root GL, m. So G and G will get cancelled. Therefore, Vp upon Vm be equal to root of Lp upon root of Lm. Therefore, Vr, which is the ratio of velocity, Vp upon Vm, will be equal to root of Lr, where Lr is the scale ratio for length. So this is nothing but the Froude's model law. Now if we go ahead and derive some scale ratios, then we would get, so we will derive some scale ratios in case of a Froude's model law. So scale ratio for time can be derived very easily as the let us say the ratio of velocity is equal to Vp upon Vm. So Vp can be written as Lp upon Tp and Vm can be written as Lm upon Tm, where L stands for length and T stands for time. So Lp upon Lm will become Lr and Tp upon Tm will become Tr. Therefore, Tr will be equal to Lr upon Vr, but we have already derived that Vr is equal to root of Lr, so that is equal to root of Lr. So scale ratio for time Tr is equal to root of Lr. Now scale ratio for acceleration Ar is equal to Ap upon Am, where Ap and Am are accelerations in prototype and model. So that can be written as Vp upon Tp into Vm and upon Tm. But Vp upon Vm is Vr and Tp upon Tm is Tr. Therefore, it will be Vr upon Tr, but Vr is equal to root of Lr, and Tr we have already derived, it is equal to root of Lr, so that is equal to 1. So acceleration ratio in case of a Froude's model law should be equal to 1. The scale ratio for force Fr is force in prototype upon force in model, and force we have derived the analogy for force as rho p Ap into Vp square upon rho m Am into Vm square. So if rho p and rho m are same, okay, still we can write this as rho r into Ar into Vr square. So that is equal to, suppose rho in the prototype and model are same, then rho r will become 1. Ar is nothing but square of Lr, and Vr is Vr square means root of Lr. So it will become square, so that is equal to Lr cube. Therefore, force ratio will be equal to cube of Lr. Lastly, we can derive the scale ratio for discharge. Qr is equal to Qp upon Qm. Now Qr can be written as Qp upon Qm, and discharge is volume upon time. So we can write Lp cube upon Tp divided by Lm cube upon Tm. So that is equal to Lr cube upon Tr. So but Tr we have already derived, it is root of Lr, so this will be Lr cube upon root of Lr, so that will be equal Lr to the power 2.5. So scale ratio for discharge will be Lr to the power 2.5. Now these are the various scale ratios for time, acceleration, force, discharge, etc., which we will have to use when we are applying the Froude's model law.